What I want to do is go through a little bit of the study guide with you. I'm not going to go through every question on this video, but the answer key is posted, so you'll have the ability to check whether or not you got certain things right or wrong. The first one I really want to look at is number 4, because it was a while ago when we did just kind of traveling waves in general as opposed to standing waves. And you're given a graph like this, and it is a displacement versus time graph right here. And we're also told that this wave is traveling at a speed of 10 meters per second. So what you're given here is you're given some information. The velocity of the wave is 10 meters per second. Whenever you're presented with a graph, basically what you may be able to get is the period or the wavelength. Basically, you have an amplitude versus time graph. And what we saw is that when we take those waves, if we look from peak to peak or crest to crest, we can get some certain information. Here, it's the time. So if I'm looking at those two peaks, this peak right here is 1 second, this one's 5 seconds. That gives me the period, which is capital T, of 4 seconds. And from that, that is our answer to A. The period is 4 seconds. What is the amplitude of the wave? If you look at how high that peak is relative to where it oscillates around, looks like it's at, if I'm eyeballing it correctly, level seems to be about 4 centimeters. And you can do that here, you can do that here. And that's what we call amplitude. How much is it displaced from the equilibrium point, which is basically, you want to think of it as a zero line here. So the amplitude, I would say, is 4 centimeters. After that, we're asked what the frequency of the wave is. That's what we want to use to get the frequency. Frequency is always 1 over the period, and if the period is 4 seconds, you're going to get 0.25 inverse seconds, or standard unit for frequency is hertz. And then once we can do that, we can get the wavelength, because the wavelength is the only thing we don't know in this particular equation. Wave speed equals frequency times wavelength, and we have our wave speed, it's 10. We have our frequency, it's 0.25. So 10 divided by 0.25 would give us a wavelength of presumably, looks like 40 meters. And that would be the complete answer to number 4. If you go skip a little bit into number 7, this is more graphical representations of waves. And you're given a graph here that shows a snapshot of each wave, or snapshot of the medium itself. Now you got 3 different medium here, or media here, and basically you can see that basically they're all different from each other. If you look at the data, it's amplitude on the left axis, and more importantly, the horizontal axis is not time anymore, it's position. So you're asked to compare these things, and it asks which one of these waves has the highest frequency. So based on that fact, when you're looking at a wave like this, a snapshot compared to something like this is the high frequency, and this is the low frequency. So you should be able to visually tell me which one is the high frequency and which one's the low frequency based on that. After that, which one has the most oscillations displayed? Again, you can see more peaks and troughs there. How does the amplitude of each wave compare? Look at how they oscillate around the equilibrium point. And based on just a quick visual inspection and looking at the numbers, it looks to me like the amplitude for each of the waves is 0.5. So I would say that they're all the same. All right, let's skip down to number 8. If you look at number 8, we give you the picture of the first harmonic, and you get that blurry view, one loop here. And we're told that the frequency of this particular wave is 10 hertz. So n equals 1. 10 hertz is our frequency. And we're asked to determine the wavelength of that wave. And in addition to that, determine the wave speed. And after that, the period. You might be able to do some things before one another. It's probably actually not going to matter what order you do them in. One thing that we want to look at in the problem is that the length of the string was given to us. It's 0.686 meters. So there's our value for L as well. Now let's just look at our formulas. Wavelength is that. And in fact, we're asked in problem A to solve for wavelength here. And so we have L and we have N. And in fact, when you're always dealing with first harmonic, we see that the wavelength is twice the length of the string. So if you simply plug in the numbers here, you got 2 times 0.686, and then the harmonic number is 1. So 2 times 0.686 divided by 1 would give me 1.372 meters. So pretty easy problem there. Determine the speed that the wave is traveling at. That's where you want to go into your wave speed equation. We have the frequency, we have the wavelength. The frequency is 10. The wavelength is just what we solved there. So it looks like it's going to be 13.72 meters per second for our wave speed. After that, what is the period of the wave? And we'll just go to frequency there. Frequency is 1 over the period, right? Our frequency is 10 hertz. So we need to solve for that denominator. Easiest thing to do for me is multiply both sides by t, because it cancels out there. So we get 10t equals 1. And then when we divide both sides by 10, we'll get 0.10 seconds is our final answer there. So essentially, solving a standing wave problem, very approachable, very easy. Shouldn't be difficult. It's kind of like just filling in a little bit of a puzzle, giving off the information that you're given. The last thing I want to do is go through number 13, because I think labeling could be important here. So when you're given just a general diagram of a wave, there's a lot of things that can be displayed here. In fact, you can look at different points in the wave and get your information. So here's our wave. It's oscillating about this point right here. We said that amplitude is right there. But you can also find it right there as well. So it doesn't matter if you go here or here. In fact, we say the amplitude is plus or minus, whatever that value you get there, because it would be positive here and negative here. Another important thing to look at is, and it depends upon what the horizontal axis is, but we already did kind of analysis of something crest versus crest here. This can be wavelength or the period. It all depends upon what this axis is. If it's in meters, it's wavelength. If it's in seconds, it's your period. But you actually don't have to go crest to crest. You can actually, let me take this just a little bit further. You can get the same measurement going trough to trough. You can even get it by looking at one full sine curve. This distance right here, or this measurement right here, would give you lambda, or it would give you the period depending upon what the axis is. So that's very important to recognize. When we look at this point here, it's usually called the zero line or the equilibrium point. Some people have different names for it. It's fine to name them, and I've been kind of saying this inadvertently. That's your crest, and the bottom is called your trough. All right, so being able to identify all these points on a wave and being familiar with those terms, I would say is very useful in working through a lot of these problems.